How's it going, everyone? We're going to do a couple of problems as examples for integration by parts, and then you guys will be able to complete the take-home quiz, the take-home Chapter 5 test tonight, and you might also want to look ahead or look back at some of the integration by parts problems that you've either done yesterday or will need to complete tomorrow. I'm going to do a couple integration by parts problems today, hopefully to answer some questions that you might have had based on last night's homework, or to show you some tricks that might be useful in doing future problems. So the first integral that we want to try to take is the integral of the natural log of x dx. Sorry for my lousy handwriting. In this case, we know that the derivative of the natural log of x is 1 over x. We're not yet familiar with what the integral of the natural log of x is, so we're going to have to be a bit creative in using integration by parts to solve this problem. Because I don't know what the integral of natural log of x is, and because there's only one term, my only option is to choose u to be the natural log of x. And the only thing left for dv would be 1, since 1 times the natural log of x would be the natural log of x. I can take the derivative of the u side of my table and get 1 over x. And I can take the integral of my dv side of the table, and I'm going to get x. One question that you might have based on last night's homework is, how do I know when to stop doing integration by parts? In some of the examples we did yesterday, the problems terminated naturally, but in this case we could continue to take integrals over here and continue to take derivatives. When we're completing the table, we want to be mindful of what the integral would be when we look across a row. So in this case, we have an integral that would be 1 over x, or the integral of the quantity 1 over x times x. So that's something that's much easier than what we started, so we could probably stop there. And that's what you want to do. You want to look through your table, and you want to look across the rows and look for a product that you can take the integral of. And then you can stop there. You don't need to continue with the table method. So I'm going to write this out. So my first diagonal is positive. The integral is going to be negative, and I know that I'm taking an integral because that's across a row instead of down diagonally. And so this is going to be equal to x ln x minus the integral of 1 over x times x dx. So in that case, x divided by x is 1, so this integral is easy to evaluate. So we've got x ln x minus the integral of 1 is x plus c. All right, and that would be my answer. So in this case, we had to be a bit creative and use dv as 1. Let's try another problem where we need to be creative as well. Alright, so you might have seen a problem similar to this in your homework last night. let's try taking the integral of e to the x sine x dx. So in this case, if we're thinking ahead, e to the x, whether I take an integral or a derivative, will always be the same. So that's not so bad. Sine of x, whether I take an integral or a derivative, once I've taken that plenty of times, I'll return to sine x. As an example, if I did the derivative of sine x, I'd get cosine. The derivative of cosine is negative sine. The derivative of negative sine is negative cosine. The derivative of negative cosine is sine. So eventually I get back to where I began. And this is an interesting thing to have happen. When that comes up, the solution for these types of integration by parts integrals has a neat trick at the end that I want to show you. In this case, we could actually pick our u and dv. It would work equally as well either way. So I'm going to pick my u to be sine x, and I'm going to pick my dv to be e to the x. So I'm going to take a couple of derivatives just like I did before. The derivative of sine x is cosine x. And the derivative of cosine x is negative sine x. And the integral of e to the x is e to the x. And the integral of e to the x is e to the x. I'm going to stop here because if I look at the table, again, I'm considering where to stop based on what my integral would be. Across the bottom row here, my integral is e to the x sine x, which is the same integral I started with. And there's something that I can do with that to help me avoid having to take the integral at all. So I'm going to complete this. So I'll have a plus there, a minus, and a plus. So let's write this out. This integral, the integral of e to the x sine x dx, is equal to e to the x sine x, that's my first diagonal, minus e to the x cosine x. And then my last entry here in the table is my integral, so it's going to be minus the integral of e to the x sine x. But these two integrals here are the same. And just like I can move other terms around an equation, I can move this integral to the other side by adding it to both sides. So I'm going to add that integral to both sides of this equation. And I'm going to end up getting 2 times the integral of e to the x sine x dx equals e to the x times the quantity sine x minus cosine x. And I can get rid of that 2 by dividing both sides by 2. And that's my answer. The integral of e to the x sine x dx is the quantity on the right. Don't forget our constant. Got our constant of integration there. Okay, so that's a neat trick that you can do when you notice that both your terms in the original integral either don't change or have some sort of periodic nature where they might return to their original term or the original term times a constant. So keep that in mind. All right, let's do another problem. In this case, we're going to try to take another integral. Let's do a definite integral since we haven't done that yet. And again, let's try to take an integral where picking the u and dv might not be quite as straightforward. So let's try the integral from 0 to 1 of the arctangent of x. So in this case, again, we only have one term, and we want to consider using integration by parts. Just like the natural log, we don't know how to take the integral of the arctangent. So really our only choice is to make arctangent u, since we do know the derivative. So I'm going to put arctangent of x right there. And again, just like in the trick from the natural log problem, for dv we're going to put 1, since 1 times the arctangent of x is equal to the arctangent of x. So now we'll go down one row in the table. We'll take the derivative of arctangent x, which is equal to 1 over 1 plus x squared. And we'll take the integral of 1, which is going to come out to be x. At this point, just like in the last two problems, we need to consider whether or not we want to go down another row, or if the integral we have is easy enough to use. In this case, I have on the bottom, I'm going to be left with the integral x over 1 plus x squared. And hopefully, I remember that that's a problem we did with u substitution. So in this problem, I can solve it by applying integration by parts here, and then using u substitution to solve the integral that I get out of integration by parts. So let's see what that's like. So I'm going to complete the table, and I'm going to find that this integral is equal to x times the arctangent of x minus the integral from 0 to 1, and this quantity over here, sorry, is evaluated from 0 to 1, minus the integral from 0 to 1 of x over 1 plus x squared dx. And I got that integral again from the last row in the table that I made up there. We've seen this integral before. If we look on the bottom, 1 plus x squared could be our u. So here we're going to do a u substitution. We're going to make 1 plus x squared our u. And so then du is equal to 2x dx. And so that this x dx shows up on the top of that integral that I'm trying to take. So I can make this u substitution. I could also quickly change my bounds, so I know that u of 0 is equal to 1, and u of 1, so here I'm using the bounds of the integral to check what my new bounds should be. So u of 0 is equal to 1, u of 1 is equal to 2. So my new integral, let me write that real fast. So this will be unchanged. But my new integral will go from 1 to 2, and I've replaced 1 over 1 plus x squared with 1 over u, and x dx is being replaced with du over 2. So I'll have du, and I'll put a 1/2 out here. Can go ahead and evaluate that integral, and we'll get the answer for the first term, pi over 4, and for the second term, we're going to get natural log of 2 over 2. Remembering that the integral of 1 over u is the natural log.